In this example, we're going to be taking a look at a linear transformation that is going to take us from the vector space R3 into the codomain of R3. So suppose we have a linear transformation, and we know that the image of the vector 1, 0, 0 is the vector 0, 1, 1, that the image of the vector 1, 1, 0 is the vector -2, 3, 1, and that the image of the vector of 0, 2, 2 is the vector 3, -1, 3. What we're going to do is find T of 5, 8, 6. Shout out to my Macomb County people. So with that in mind, first thing I'd like to do is just do a little bit of labeling. 1, 0, 0, we're going to label it as V1. Its image will be W1. 1, 1, 0, we're going to refer to that as V2. Its image we refer to as W2. And finally, T of 0, 2, 2, we're going to refer to 0, 2, 2 as vector V3 and 3, -1, 3 as vector W3. That way we can abbreviate this to be simply T of V1 is equal to W1, T of V2 is equal to W2, and T of V3 is equal to W3. Now the idea is I would like to express 5, 8, 6 as a linear combination of V1, V2, and V3. If we're able to do so, then we can express that linear combination in terms of the pre-image, send it through the vector, and get the image in terms of our W vectors. So we're going to turn 5, 8, 6 into a linear combination of V1, V2, and V3. Once we do so, we can apply properties of linearity to express this as C1 times T of V1 plus C2 times T of V2 plus C3 times T of V3, which will allow us to express this as C1W1 plus C2W2 plus C3W3. Now this all starts with our ability to express 5, 8, 6 as a linear combination of V1, V2, and V3. So let's start there. So we'll say C1 V1 plus C2 times V2 plus C3 times V3 is going to be equal to 5, 8, 6. Now if we set these corresponding components equal to one another, the first component is going to be C1 plus C2. And that's going to be equal to 5. The second component will be C2 plus 2C3. That's going to be equal to 8. And then for the third component, I'm seeing 0C1, 0C2, and 2C3. And that'll be equal to 6. Now, if we wanted to go the matrix route, I just want to point out, that the first column would be vector V1. The second column is vector V2. The third column is vector V3. That'll be important in the next video. Then what we're setting it equal to, that is going to be our augment. Well, I'm pretty sure that I'm going to be able to solve this without the use of reduced row echelon form. This last equation here implies to me that C3 is equal to 3. And if we plug that into this equation and solve for C2, we'll get C2 is equal to 2. If I plug that into the first equation and solve for C1, that'll give me C1 is equal to 3. So again, this is where we're going to go through this route right here. So what we're saying is that the image of the vector 5, 8, 6, this is going to be equal to the image of 3 times V1 plus 2 times V2 plus 3 times V3. Let's just verify real quick. First component, 3 times 1 plus 2 times 1 plus 3 times 0, that's 5. Second component, 3 times 0, 2 times 1, 3 times 2, add them up, that's 8. 3 times 0 plus 2 times 0 plus 3 times 2, that is in fact 6. Then we can apply the properties of linearity to say that this will be 3 times the image of 1, 0, 0 plus 2 times the image of 1, 1, 0 plus 3 times the image of 0, 2, 2. borrowing those images from the description of the problem, that's W1, W2, and W3, this is going to wind up being 3 times the vector 0, 1, 1, plus 2 times the vector -2, 3, 1, plus 3 times the vector 3, -1, 3. Once we perform this linear combination, we will have our image. Let's go one component at a time. For the first component, I'm seeing 3 times 0, 2 times -2, and 3 times 3. That's 0 minus 4 plus 9. That'll be 5. For the second, 3 times 1 is 3, 2 times 3 is 6, 3 times -1 is -3. We can cancel the -3's to get a 6. And for the third component, 3 times 1 is 3, 2 times 1 is 2, plus 3 is 5, 3 times 3 is 9, plus the previous 5, that'll be 14. So here is the image of our vector.